just got financial aid. His son in financial aid. And the students were getting loans, not even seeing money. They were still paying. Now, you can honestly say, I got financial aid.
Oh, that's awesome.
They added two.
Yeah.
And it's only like not even 7.2. This right here, this one right here, cost about. This one's a handicap one. It turned from a 4x4 pan, plastic pan, and the guy doesn't. The old man doesn't have no legs, so it's amputated. And how to make it in a walking shower.
Oh wow.
Yeah. So. See.
Oh, that's very cool.
Yeah. I'll show you this. Check this out. This we did for the sun. I don't know if you have a sunroof or sunroom or anything. But this, what it looked like before, it was really bad. Like the cedars all molded, now it looks like this.
Oh wow.
So, yeah. Extreme header. Like the roof. Yeah, like putting on the roof just like a cover, right?
All right, y'all ready? So let's talk about negative exponents. Let me give you an example of what a negative exponent looks like. It's an exponent with a bad attitude. So, negative exponent. You would think. Actually, the answer is 1/9. The answer is 1/9. When you have a negative exponent, the way that you solve that problem, meaning the way you make it positive, is that if you have a negative exponent in the numerator of a fraction, you move it to the denominator. And if you have an exponent in the denominator, you move it up to the numerator. So, for example, 3 to the negative 2 power, we could rewrite as 1 over 3 to the positive 2 power. Now, the reason why is that the negative 2 was in the numerator. We don't really write it, but you can write any number as a fraction by putting it over 1. So we just moved it from the numerator into the denominator. That causes the exponent to change from positive to negative. Okay? So what's the answer? Well, 3 squared is 9. That seem all right? Now, it's important to notice that in this problem, the x is the only thing with a negative exponent. The 2 does not have the negative exponent. If I wanted them both to have the negative exponent, 2 and the x, I'd need a set of parentheses. No parentheses here, so only the x has the negative, which means when I move stuff, only the x moves. So what's this going to look like? Well, The 2 was in the numerator, and it stays in the numerator. I didn't have any problem with the 2. The problem was the x. X to the negative third power now drops down into the bottom and becomes x to the positive third power. Let's do some addition. So 2 to the negative first power is really 1 over 2. And 4 to the negative first power is 1 over 4. You can get a common denominator and add those if you want to, but I know my bakers in the class already know the answer. What's a half plus a fourth? Half a cup plus a fourth a cup? Really? Nobody bakes? A half is 2/4. So 2/4 plus 1/4 is 3/4. Your homework is for somebody to make muffins for class next week, so you can practice your. I mean, it's all for education. It's all for education. Bring some muffins. I like cranberry walnut. So. Oh, you don't get to decide what the homework is. Cranberry walnut is the assignment. If you want to make something else, that's your problem. Homework, cranberry walnut muffins. Or scones. I don't actually know what a scone is, but I've always wanted to try one. So, y to the negative fourth would be? There we go. 1 over y to the fourth. Nailed it. This also works in reverse. If the negative exponent is in the denominator, like that, the way we make that positive is by shooting it up into the numerator. So 1 over x to the negative third power would become just x to the third power, right? It's x to the third power over 1. You move this up into the numerator, which leaves the denominator empty. If there's nothing in the denominator, it's 1, but there's no reason for us to write the 1. Okay? Just like before, only stuff with the negative exponent moves. So the 3 in the numerator, I got no problem with the 3. He's fine. No negative exponent on that guy. I got a big problem with the x to the negative fourth. How do I fix that? Three x to the fourth. Good. Huh? That one's pretty good, I'm not gonna lie. It's pretty great though. What do you think? I didn't hear what you said. We just did these a few minutes ago. Yes. When you've got them divided, what do? You subtract. That's exactly right. So this is x to the negative fifth minus 7, which is x to the negative 12th, which is there you go. Good. Okay. And just to make the whole thing complete, let's do one with a fraction. I don't know why I decided that negative 3 needed to be in a different color, but what's done is done. I hear lots of mumbling. 2 to the... Let's take it one step at a time. This is quotient rule. You've got a fraction inside parentheses raised to a power. Everything in the parentheses gets that power. There we go. So 2 to the negative third over 3 to the negative third. Now, if it's got a negative exponent, we move it, and here we've got to combine both rules we just talked about, because we've got a negative in the numerator, that one's got to be dropped down to the denominator, and we have a negative in the denominator, that needs to be moved up into the numerator. So let's do that next. 2 to the negative third comes down into the denominator, where it becomes 2 to the positive third. And then the 3 to the negative third in the denominator comes up top to become 3 to the positive third. Those are both numbers, and they're both small enough where I think we could just do them, right? 3 to the third is 27. And 2 to the third is 8. That won't reduce, so we'll just leave it like that. Okay. Yes? Okay. I will take your silence as a wahoo. I really think it's best in these situations where they start to get really complicated and there's like clearly multiple exponent rules going on. It's usually best to save the negatives till the end. Because sometimes as you're working through the other exponent rules, the negatives will sort of take care of themselves. So let's just forget about the negatives for a second. What would I do if this was all positive numbers? Both things in the parentheses. You don't add the exponents. This is power of a power. It's y to the negative third to the negative sixth. It's y to the positive 18th. You multiply them. Okay? And then x to the sixth to the negative sixth, x to the negative 36th, which is fine. But we've got a negative. Let's take care of that. Yep, so, well, not all of it, because the y is fine. Yeah, just the x. So the y to the 18th could stay. It's the x to the 36th that's got to come down. I can't reduce that because one of them's an x and one of them's a y. If they were the same variable, I could probably do some work, but they're not, so I can't. Sorry, kids, I don't make the math rules. Sometimes no is the answer. Now what? Why do you do that? Why do you keep adding the exponents? Are you trying to hurt my feelings? Okay, so yeah, it's x to the 12th, but also 2 to the 4th, x to the 12th, and then the other x. So that will eventually be x to the 13th on top, right? Right, this was power of a power, so I multiply. All right, what I'm actually going to do next is this is product of powers, x to the 12th times x to the, there's a little 1 right there. So 2 to the 4th is 16, x to the 13th over x to the 7th. And you were talking about this on the last problem. You said, oh, reduce it. I can this time. I can reduce it. Because the variables are the same, they're both x's. So I can go ahead and put this together. The 16's fine. X to the 13th over x to the 7th is x to the 6th. You subtract it. All right. Who's ready for a nightmare? This one is not going to equal 1, but boy, I sure love where your head's at right now. Look at all the negatives. So there actually aren't any other exponent rules in this problem. There's no parentheses, there's no like power of a power. The only stuff we have to deal with right now is the negatives. So let's start with that. I'm just going to do things one at a time, and I'm going to decide as I go through this problem, does this thing need to move, yes or no? So let's start with the first one. 4 to the negative first, does it need to move? Yep, because it's negative, so 4 to the positive first down here in the bottom. Okay, next, x to the negative third, does it need to move? Yep, so x to the positive third down here in the bottom. Then y, does that need to move? No, that's got a positive exponent. He can stay put. Okay, let's move to the bottom. 4 to the negative third, does it need to move? Yep. X squared? That one's fine. Y to the negative sixth? Yes. So the problem that we have now is still kind of a disaster, but it is a disaster with no negative exponents, so progress? Now what? Yeah, we can combine the y's and the x's. So let's go ahead and do 4 to the third. 4 times 4 times 4, 64. Y and y to the sixth gives us y to the seventh. Now on the bottom, 4 to the first is just 4. X cubed, x squared gives us x to the fifth. Great, great. Are we done? No, because 64 fourths will reduce. What will 64 fourths reduce to? It'll reduce to 16. Where does the 16 go? Does it go on the top with the y's, or does it go on the bottom with the x's? Okay, great. Those are two very wonderful guesses that were not backed up by anything. So I think that's all the debate we need. Let's just vote. 16 over 4 doesn't actually reduce to 16. It reduces to 16 over 1. So 16 over 1. We don't write the 1, but it's there. All right. Now, I think a perfectly reasonable question to ask that not one of you people has bothered to ask me yet is, who cares about exponents? Why do we need that? And I like to think that the reason that you're not asking me is because you've been conditioned over years of math education to know that my answer is going to be baloney. But in this case, I actually have a good reason why we need exponents, and it's not like in case you're an engineer or an architect or whatever. Exponents are really valuable, and one of the ways you've seen exponents are really valuable is when they're giant. When the exponents are really, really huge, it's handy to know what exponents are. If it's 10 to the 27th times 10 to the 94th, that number is so huge that the calculator won't even do it. So we leave our answer in exponents. So what is a practical application of needing to leave your number in exponents? When would you ever need to do that? And I hope you're paying attention. Nurses and astronomers. Have you heard of scientific notation? Scientific notation, and I don't really like that it's called scientific notation. I think it should be called mathematical notation because we shouldn't give science credit for stuff. But scientific notation, which the scientists probably stole from us, is how you can represent really, really enormous numbers or really, really teeny tiny numbers using exponents. Let me give you an example of an enormous number. When I ask people to rate my looks on a scale of 1 to 10, this is usually the number they come up with. This is 367 million. This number isn't that bad, right? It's a 367 and 6 zeros. It didn't take me that long to write it. But I want to show you how you can convert this into scientific notation with a very quick and easy 3-step process. So first of all, where is the decimal in this number? Yeah, right there. But we don't really write it because there's nothing after the decimal, but it's right there on the end. Step 1 is move the decimal until the number is between 1 and 10. So where would I have to put this decimal so that instead of 367 million, I get a number that was between 1 and 10? 367 is not in between 1 and 10. Yeah, what about 3.67 with 6 zeros? Now my number is between 1 and 10. It's 3.67 with a ridiculous number of zeros. Step 2, count how many places you moved the decimal. So when you move the decimal, you're going to move it in one of two directions. You'll either move it to the right or you'll move it to the left. That makes a difference when you're counting how many places. If the decimal moves left, it's a positive number. If the decimal moves right, it is a negative number. So in my original number, which was 367 million, I now have the number 3.67. How many times did I move the decimal? Well, I moved it 1, 2, 3, 4, 5, 6, 7, 8. I moved it 8 times. And I moved it to the left. So I'm going to call it 8 instead of, if I moved it to the right, I would call it negative 8. Okay? Step 3, multiply the number in step 1 by 10 raised to an exponent equal to step 2. So, what was the number that I came up with after step 1? That was step 2. 3.67 multiplied by 10 raised to the number that I found in step 2, which was 8. And there it is in scientific notation. 3.67 times 10 to the 8th power. We represented 367 million in a way that is intelligent for a couple of reasons. Number one, it's easier to read. If I didn't tell you, if I hadn't said out loud 367 million, the way you'd have to figure it out is by counting the zeros. If only 6 zeros, probably not that big of a deal. If I had like 25 zeros, it'd be hard to even tell what that number was. And the second reason is it's easier to say. 3.67 times 10 to the 8th is much easier than 367 million. So, if you're going to deal with very, very large numbers, the most obvious one is astronomy because everything's so far away. Scientific notation's great. What if you're going to deal with teeny, 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 tiny numbers, nurses? What number is that? When you have all those zeros in a row, like they start to blur together and it's hard to even read the number. Like, is that, it looks like 5 zeros? Is it 6 zeros? It's hard to tell how many there are after the decimal. You still follow the same steps though. Step number 1, move the decimal so that the number is between 1 and 10. Here's the decimal right there. Where would I have to move it so that the number was between 1 and 10? Just tell me where, like in relation to these numbers, where would it be? After the 3. So my number would be 3. Step 2, how many places did I move it? Well, it went 1, 2, 3, 4, 5, 6 places to the right. So moved 6 places. And so step 3 is take the number from step 1, which is 3, multiply it by 10 raised to the power of what you found in step 2. So step 2 was 6, but I moved it to the right, so negative 6, and there's my number, 3 times 10 to the negative 6th. This is useful in the medical field because the dosages that you give people are typically very, very, very small. Very small dosages. And so these numbers are much more useful than a decimal saying, well, it's 0.0000000000000. It's much easier to say 3 times 10 to the negative 11. Then you know how many zeros they're supposed to be. Okay? Let's do a really giant one. I like big numbers and I cannot lie. Right now, the decimal's on the end of the number. Here's the decimal. Where would the decimal have to be so that the number was between 1 and 10? After the first 2. So what would that number be? 2.052, and then a whole bunch of zeros. I'm not going to write the whole bunch of zeros because it doesn't change the number, but you get the idea. How many places did I move it? 4, 5, 6, 7, 8, 9, 10. 10 to the, and is it going to be positive 10 or negative 10? Positive because I moved it to the left. So there it is in scientific notation. Okay, let's do another itty bitty. Here's the decimal now. Where does the decimal need to be so that my number is between 1 and 10? What about the 5? Between the 8 and the 5. So what would my number be? 8.5. How many spots did I move it? 4, right? So times 10 to the 4th, but I moved it to the right, so negative 4. So, being able to convert a really giant number into scientific notation is useful to us. It's a good way to represent a really big or really small number in a little simpler way. But equally useful is the ability to go the other direction. Meaning, if I give you a number in scientific notation, could you turn it into the regular number? We call it standard form. Is there a way that I could turn it into the regular number? Remember what the exponent is telling you. The exponent is telling you how many times to move the decimal. So when it's times 10 to the 5th, how many times am I moving the decimal? 5 to the right or the left. Oh, be careful. I did move it to the left. So to undo it, I'm moving to the right. So the decimal moves 5 places to the right. Okay, fine. So I take 1.02, and here's my decimal, and I move it 1, 2, and I can't move it anymore because I'm out of numbers. Start adding zeros. 3, 4, 5. So my number is 102,000, 102,000. That seems all right. Is this number, when I'm done writing this and it's in standard form, is the number going to be a big one or a small one? Yeah, a small one. How do you know? Right, the negative exponent means it's going to get smaller. So the decimal is going to move to the left. Good. So it's 7.358. Here's my decimal. 3 places to the left. So I go 1, and then I'm out of numbers, so I gotta start adding them. 2, 3. So my number is 0.007358, and because we are good mathematicians, we follow good math conventions and put that 0 placeholder out in front, just like that. Okay? Is this number going to be bigger or smaller? It's going to be big. So it's 8.4, and I'm going to move the decimal how many places? 7 to the right. So there's 1. Start adding numbers. 2, 3, 4, 5, 6, 7. My number is 8, 4, 6 zeros, 84 million. The amount of money people say they would pay for the knowledge they gain in this class, which makes your tuition a bargain. You are welcome. Let's do one more of these. To the left, good. 3.007. Here is the decimal. So we go 1, 2, 3, 4, 5. And there's the decimal. So 0.1234. Okay? So the last thing that we're going to talk about is how to do operations with scientific notation, meaning can you multiply and divide numbers that are written in scientific notation? Spoiler alert, yes you can. There's an example. Performing operations with scientific notation. I'm going to give you one multiplication one and one division one. Now, even though it looks like this is one pretty awful multiplication problem, when you get something like this with scientific notation, treat the tens like they're variables, by which I mean multiply the just plain numbers first and then multiply the tens. And the reason we're going to do that is because 8 and 7 will not follow the exponent rules, but the tens will. They've got the same base. That means they follow the exponent rule. So I'm actually going to use one of our properties here to just group these up in a different way. This is called the associative property. I'm sure you remember this from last semester, right, kids? Multiplication can be done in any order, so I haven't changed the problem yet. I'm just illustrating that I'm going to group up the plain numbers together and the tens together, and here's why. 8 times 7 is pretty easy. That's 56, right? Times, what's 10 to the negative 6 times 10 to the third? Well, that's power of a power. Oh, sorry, that's product of powers. What do you do with the exponents? Yeah, you add them. 10 to the negative third. Good. That is not scientific notation. Why not? There is. It's after the 6. For scientific notation, what does the number have to be? It's got to be between 1 and 10. 56 is not. So scientific notation, I would have to move the decimal one more place to the left. Moving to the left causes me to lower the exponent, so that would be okay. It'd also be okay to write it in standard form, which would be 0.056. Is that right? Nope. Oh, this is 0.056. Did I mess up? Oh, this should be derp. That's -2. Sorry, kids, I can't add. You're in good hands. Okay, let's do a division one. That one pretty much functions the same. And when I say it functions the same, what I mean is treat the numbers like their own thing, and then treat the exponents like their own thing. So let's start off with the 12/6. That's pretty easy. What's 12 divided by 6? This is 2. Simple. And then what about this? Yeah, subtract. So times 10 to the 2 minus -3. That's 2 times 10 to the 5th. This is an okay answer. You could also write it in standard form. Yep. So make sure you pay attention whether the answer is being requested in scientific notation, which would be that one, or standard form, which would be that one. Does anyone have any questions about anything?